Hello. Hi, Araceli, you there? Araceli, I can't hear you.
Oh, sorry.
That's fine.
I'm here.
That's fine. Do you have any questions, Araceli?
No, I just arrived early, but I mean, I do have one question.
I'm here.
I checked in the email that you sent on Sunday, I think.
Okay.
And it said something about an extra credit opportunity for the homework for the mastering chemistry.
Yeah, there is a there is a chapter, and if you look at the assignments, it's called
Mhm.
Introduction to Mastering Chemistry. You were supposed to do that before you started the Pearson thing, because basically what it does is it tells you how to do things like put the molecules together. Literally speaking, what you're having to deal with I think it's the last homework.
Oh, okay.
So if you go in and do that, if you get points in that, all those points are considered extra credit.
Okay.
All right.
Thank you.
No problem. Stick around. I'm going to go back to grading some quizzes, but if you don't have anything else, then I will definitely be starting at 10:15. Okay.
Okay. Okay.
Damn it.
Morning, Professor.
I'm sorry, Jana. I'm right in the middle of grading quizzes. Do you have any questions?
No, I don't. I just wanted to say good morning.
Did you look at the rubric before you did the presentation? I tried to warn
Yes.
you guys. Okay, good, good. Basically, you
Yes,
got
we did.
you got at least a B, Jana.
We
And
Hmm.
putting any sort of effort into this, you'll probably get an A.
Well, I surely do hope so. We worked on it like for a long, long
I
time.
know. My wife was starting to get irritated.
I'm I'm really sorry. I
No,
felt
no,
really
no.
embarrassed keeping
No,
the
no,
call.
I'm sorry, she was getting irritated. I wasn't. So as she answered the phone, her voice level was getting more and more irritated. She actually told me to give you guys 3 golden tickets. In other words, you had 3 phone calls, but it's all for the better. Okay. We got through it. All right.
Yeah. Yeah, we did. Now it's just a matter of hopefully we did everything great.
I'm sure you're going to do fine. I'm sure, I mean, as conscientious as you guys are, I'm sure you guys are going to do fine. All right. I'm not
Yeah.
worried about it, so you shouldn't be. Yeah, I got to do one more thing and then I can get to you all. I got to write an email to my class in SCP. This is what happens when you don't edit well. Okay, I'm sorry, guys. How we doing? We doing okay? Jenna, you just popped in. Do you have a question, Jenna?
No, I'm just chilling, hanging out.
Okay, did you take the test yet?
No, not yet. I'm gonna
Okay.
take it in person. Yeah.
Yeah, thank God. Jordan already found found the problem because I didn't realize that the guy that made the quiz, I didn't
Mhm.
realize he put an access code in there. So
Oh, interesting.
so basically she was stuck and had to call me and I had to take it away. So you should be okay.
Gotcha.
She was able to log
Okay.
in. She was able to log in after that. So everything should be good.
Okay.
Anybody have any questions? Any questions? Natalia Sachari, did you look at the rubric for the presentation? I see Natalia shaking her head.
Yes, did our best.
Okay, because that's what I'm grading on, all right? What do you have, trail mix there, Natalia?
Huh?
What are you eating, trail mix?
I'm eating honey bunches,
Straight,
cereal,
milk or not?
milk. Yeah.
Okay, all right, good enough. Me, I'm gonna be having a sandwich on the way from St. Petersburg over there. No wonder I have stomach problems. What can I say? Anybody have any questions on electrochemistry? We're pretty good. We know a cell. We know the different parts of a cell, and we're going to be able to describe it. He said, nudge, nudge, wink, wink. We have that down, guys. That doesn't seem too confusing. We have the balancing of redox equations down. I'll be honest with you, last test, that was one that most of the students just gave up on. So just make sure you know how to do that. So I'm just here tap dancing until I get 10:15. Then we got to start it sharp because we have to get through electrochemistry today, and we have to get through the types of nuclear chemistry, nuclear decay, so that we can finish up on Thursday. That does look good, Natalia. Did everybody get the note about the post lab? Or I'm sorry, the pop quiz, second pop quiz?
Yes.
Okay, the trouble is, in order for me to see that you submitted something, you have to put some sort of response in the text boxes. And Benita has already found the problem with that. But that's been corrected. So all you have to do, you have to type in something into each text box. No response is good enough because I can't require you to answer this. I do use the answers to change my curriculum. So we got ether stirring up. 4 more minutes till showtime. Don't you just hate sitting in the seats waiting for the band to start? Ugh. You're back, Araceli. I see that. Sachari, put on your image. Put on your camera. Natalie.
I'm getting ready right now. I'll turn
All
it
right.
on.
No problem. Natalie, you and Sachari, Sachari said that you were able to look at the rubric for the presentation. Is that true?
Yes,
Yes,
I was.
Professor.
We went over it.
Okay, good enough. I just wanted to make sure you had everything in there. 3 minutes till showtime. Got to find the waterfall. Nope, waterfall's down further. There we go. When you're dealing with what you're studying for the test, don't worry so much about the electrochemical cell notation. Make a note in there. Don't worry so much about that. The reason I included it is sometimes on problems, they will set the problem up like this. And you have to go from the bottom step to interpret it to mean this is what it means. Does that make sense, guys? So I wanted to make sure you knew that just in case you encountered it in any problems. Benita, you in? Benita? Hi, Benita. I heard you a second ago because I heard kids.
What did you say?
I said, hi, Benita.
Hi.
Hi. I wanted to thank you for telling me about the problem with the pop quiz.
Oh, yeah, no problem.
What happens is I just made up those first 2 questions. I just made them up and the default is multiple choice.
Oh, okay.
So if it's multiple choice, then you don't get a chance to answer.
Right.
If you feel like it and you want to comment on those, send me an email after the class, okay?
Okay, perfect. Thank you.
To be honest, I kind of forgot what those 2.
What's that?
To be honest, I kind of forgot what those 2 were. I might need to like go back to see.
Did you, I'm sorry, I thought that, is that Ethan?
Yeah.
I'm sorry, I didn't see that you entered the response as well. Guys, don't worry about it. You're going to get credit no matter what, all right?
Okay.
And as I said, I do look at that and it does change curriculum. Okay. Would you all agree? Would you all agree that when you have a waterfall, the water only goes in one direction? Would you agree with that? Shake your head. Come on,
Yeah.
Natalia. Thank you, Ethan. All right. Now, in this much the same way, electrons are only going to spontaneously go in one direction. They're going to go from the anode to the cathode. So if you have two cells and you connect them, it's going to depend on what's in the cells, what's going to be the anode and what's going to be the cathode, because that will determine which way the electrons are going to flow. They're going to go from a higher energy to a lower potential energy. And the difference in that is called the electromotive force. You can refer to that as also the cell potential. And the overall cell potential is E subscript cell. If you are talking about a standard cell, what that means is that the reaction occurs at 25 degrees Celsius, room temperature, and it has 1 molar of the ions in solution. You guys have said that you understand the cell. So you know that if you have a copper electrode, it has also copper ions in solution. If that's linked to a zinc electrode, the zinc electrode has zinc ions in solution. So if I'm dealing with the standard cell potential, the concentrations of the zinc ion and the copper ion have to be 1 molar. Now, when you're measuring current, it's measured in a substance known as amperes. And an ampere is defined as 1 coulomb per second. If you have a mole of electrons, if you have a mole of electrons, that's equal to 96,485 coulombs. This is known as Faraday's constant. Michael Faraday was a person that was a chemist that was very influential in the introduction of electrochemistry. So when you're influential, you get a constant named after you. So I have a problem here. How many grams of silver can be deposited from 10,000 coulombs? I have to know a couple things. I have to know that silver has only one ion form, and that is Ag plus 1. If I'm depositing silver, that means that I am taking ions out of solution, reacting them with electrons to make the metal. So I have a formula of Ag plus 1 plus an electron making silver metal. All I got to do is I simply know that I have 10,000 coulombs. This is nothing more than dimensional analysis problems. If I have 10,000 coulombs, I can turn that into moles of electrons by multiplying that by, I rounded that up. You can use, if you really want to be specific, you can use the 96,485. But since I was only dealing with one significant figure. I just rounded that to 96,500. Now, I've done that first equation. I now have moles of electrons. You got to ask yourself, what's the ratio between moles of electrons and moles of Ag? It's 1 to 1. So then simply I multiply it by that molar ratio. I get moles of Ag. I simply then multiply that by my molecular weight over 1 mole, and I get 11.2 grams. Really, this is nothing more than what you've already learned in Chem 1 way back when. Dimensional analysis plus a little bit of stoichiometry. Calculate the time required for 105 grams of gold to be deposited from AuCl3 by a 5 amp current. Natalia,
Yes.
AuCl3, what's the charge on the gold?
+1. I mean, sorry, +3.
+3. So what's my equation? What is my reduction equation? Au plus 3 is going to Au. So how many electrons do I have to add?
3.
I got to add 3 electrons. Okay. Now, I have 105 grams. That's how much I need to deposit of gold. So I need to change that into moles of gold by dividing by the molecular weight. Then I have to realize that I have 3 moles of electrons that are created that need to be used up for every 1 mole of gold. So I have my molar ratio 3 to 1. I then change it into coulombs by the ratio of 96,500 coulombs for 1 mole of electrons. At this point, my moles of electrons have canceled, my moles of gold, and my grams of gold. At this point, I have coulombs. The thing you need to realize, if 1 amp is 1 coulomb per second, if 1 amp is 1 coulomb per second, then 5 amps are going to be 5 coulombs per second. If I have coulombs at this point, I simply put 1 second over 5.00 coulombs, and that ends up being 30,900 seconds. Questions? Questions on this, ladies and gentlemen?
Is it normally always 1 or like 2 or 3 coulombs per second?
No, that is by definition, Manuel. That is what a coulomb. That is what an ampere is. An ampere, 1 ampere is 1 coulomb per second. So
Okay.
5 amperes is going to be 5 coulombs per second. Does that make sense?
Yes.
Any other questions, ladies and gentlemen?
Where did you get the 96,500?
That is the relationship. That is Faraday's constant. And Faraday has set this label, this thing that he's called coulombs. And he has said that there are 96,485, to be exact, coulombs are equal to 1 mole of electrons.
Oh, so you like it's rounded, right?
I'm sorry, Natalia?
Is it the same thing as the 96,485?
It's the same
Oh,
number.
Okay, okay.
I just rounded it.
Okay, okay.
You see 3 sig figs. I just rounded that to 3 sig figs. It's not really going to change the answer that much.
Okay.
And in the end, you would have to round it to 3 sig figs anyway. Any other questions, ladies and gentlemen? We're going to deal with another type of problem. You can determine how much of the metal can be deposited. How many grams of silver will be deposited on a cathode in 1 hour by a current of 1.50 amps? All right, we know that an ampere is equal to coulombs per second. So if we have a time, we can turn that time into seconds, multiply it by the amperes, and get the coulombs. We can then use the ratio of 96,500 coulombs per 1 mole of electrons to get the coulombs. Or excuse me, to get the moles of electrons. Once we have the moles of electrons, we know the ratio between the electrons and the metal. That will give us moles of the metal, which we can then use the atomic weight to get the grams of the metal. So simply speaking, first thing we have to do is we have to take the hour, multiply it by 60 minutes per hour, and multiply that by 60 seconds per minute. If you do this enough times, you'll understand that 1 hour is equal to 3,600 seconds. Okay, so I'm going to take my amperes, which are coulombs per second, multiply the time by the time in seconds. Then I'm going to multiply it by my moles of electrons per coulomb, by my molar ratio next, and then by my grams per mole. I do the math on it. Notice all the labels cancel out except for grams of silver. In a way, guys, this is just a glorified dimensional analysis problem with a little bit of stoichiometry in there. Any questions on cell plating out? Any questions on determining time from how much was plated out, or determining how much gets plated out from time? Talk to me.
Oh, I had a question. How could you explain one more time how you found the ratios? So, like, for example,
Okay,
like 1 mole of Ag for 1 mole of electron. So,
okay, Manuel. What's the only charge that silver can have?
+1.
So in order to plate out the silver, I need to turn the ion of silver into the metal, correct?
Okay.
So how many ions do I have to add to silver +1? How many electrons?
1 to make it neutral.
Yeah, that's what you're doing. You're making it
Okay.
neutral. So you're taking the ion, making it neutral. If you remember from this one, I had Au plus, sorry, trying to go back a slide. I had Au 3 plus 3 electrons. So my relationship between the electrons and the ion are 3 to 1. Or if you want to do it,
Oh,
3 moles of electrons to 1 mole of the neutral metal.
okay.
That's
Gotcha.
why I said you had to use a little stoichiometry in this. You good,
Okay,
Manuel?
Gotcha. Yeah, I got you.
Okay. Any other questions, guys? Anything else?
Professor, I had a question.
I'm here.
I was just a little bit confused on the part of the 1.00 H times 3600 seconds over 1 hour. Like, are we converting some, or like the seconds, or
Yeah,
that's
that's all you're doing. Araceli, you're multiplying 1 hour by 60 minutes over 1 hour, and then you're multiplying that by 60 seconds per 1 minute.
okay.
60 times 60 is 3,600.
Oh, okay.
Any other questions, guys? Okay. Now, we're going to have to deal with another label, and that is volts. When you have electricity, can you do work with it? Can you do work with electricity?
Yeah.
So if you're doing work, you're doing energy. You need to have a joule. You need to have joules in there somewhere. So by definition, we've decided to say that 1 volt is equal to 1 joule per coulomb. And we have developed tables. We have developed tables which are going to tell you, they're going to relate one reduction reaction with another. If you notice the table we have here, we're adding electrons to the left side. If we're adding electrons, that means that we are reducing. We're having reduction. So when we do a reduction and we determine how many volts there are, that is called a reduction potential. This, because it's standard reduction potentials, it's done at 25 degrees Celsius, and the molar values of the solutions that the electrodes are in are 1 molar each. So we've tabulated all these, but in order to tabulate them, we have to compare them with something. We compare them to something known as the standard hydrogen electrode. By definition, the reduction potential for hydrogen is 0 volts. So if we have 2 H pluses plus 2 E's going to H2, we're just saying from the very get-go, this reaction, if I have 1 mole of acid in solution and it's at 25 degrees Celsius, I'm saying this is going to be 0 volts. Now, what I'm going to do to this is I'm going to attach another cell to this. And depending upon how many volts I create from that other cell attached to the hydrogen, the standard hydrogen electrode, that is going to give me the value that you see in this table. So, for example, when I hooked fluorine at fluorine gas going to fluorine ion, when I hooked that up with a standard hydrogen cell, the difference in potential was a plus 287 volts. When I hooked zinc up with my hydrogen, I got a negative 0.76 volts. Are we good with that? Do we understand where those numbers came from? Somebody give me a yes. Any questions? Guys, it's hard when you don't respond. Somebody tell me you understand, or if you don't understand, ask a question, please.
We understand.
All right. Now, in order to get a spontaneous reaction, my E0 cell, the difference between my oxidation and reduction reaction, has to be a positive number. I determine that by determining the E0 that occurs at the cathode, the reduction reaction. I add to that the E0 of the anode reaction, the oxidation reaction. So what I'm going to do, I want a positive number. So if I'm reacting copper, if copper is in one cell and iron +2 is in the other, bottom line, I have to get a positive number out of this. I can't have 2 reduction reactions, so one of these reduction reactions has to be flipped to be an oxidation. I have to figure out whether I'm going to flip copper to be an oxidation reaction or I'm going to flip iron. The result, when I add them up, needs to be a positive number. The reduction potential for copper is 0.34. It's a positive. The reduction potential for zinc is a negative 7.6. And the other thing you have to know is that when you flip the reaction, you flip the sign of the potential. So which one am I going to flip so that when I add them, I am going to get a positive number? Am I going to flip the positive 0.34 or the negative 0.76?
The negative?
I'm going to flip the negative 0.76. So what that means is when I put a zinc cell with a copper cell, the copper is going to be reduced, the zinc is going to be oxidized. And the standard cell potential is going to be the addition. Since I flipped the zinc, this number now becomes a positive 0.76. I add that to the 0.34. This gives me a standard cell potential of copper and zinc of a positive 1.10 volts. Now, I just said a lot there.
If they're both positive, can we just like go ahead and add them?
No, absolutely not. The reason you can't do that is one has to be an oxidation reaction. You cannot have a reduction reaction without an oxidation reaction. So you have to flip one. So if I'm going with silver and copper, both of those are positive. I have to flip one of those reactions. Now, which do I flip?
The 0.34, because it's the lowest one.
And when I flip that reaction, that makes a new standard oxidation potential of a negative 0.34.
Right.
I then add that to the positive 0.80 and I get a positive 0.46. Other questions, ladies and gentlemen?
And the same thing happens for if they're both negative, right?
Well, you would flip the other one, Natalia. This one, when you have two positives, you flip the smaller number.
Right.
When you have two negatives, you flip the
The biggest
larger number.
negative number.
So for example, if I have aluminum with lithium,
Yes.
I'm going to flip the lithium.
Right, because it's the biggest negative number.
Right. The bottom line is I need to end up with a positive number. I have to flip the reaction that will give me a positive number.
Right. Okay.
All right. I'm going to see if I did something. The other thing I need to point out is it's based upon potential energy per unit of charge. So it's an intrinsic property. It doesn't matter. At this point, do you remember when you did like Hess's law? That was a state function. So when you did Hess's law, if you multiplied the whole reaction by 2, you had to multiply the enthalpy by 2. Do you remember that, ladies and gentlemen?
Yes.
Okay, this is different. This is an intrinsic property. This means if you multiply the reaction by 2, you do not multiply the voltage by 2. The voltage stays the same. We're going to deal with that factor later on when we talk about the Nernst equation. But for right now, if you double the equation, you do not change the quantity of the voltage. And I'm hoping, all right, good. I did point that out. Now, this is the way I'm presenting. I am presenting this in this fashion because I think it makes more sense. You're going to have to flip the reaction anyway. You might as well know that when you flip the reaction, you change the sign of the potential to have an E oxidation, so that when you flip the reaction, you are adding the E0 of the oxidation with the E0 of the reduction. How you are going to see it in books and how it classically is presented is that the E cell, E0 cell, is going to be the E reduction at the cathode minus the E reduction at the anode. In other words, if you're using the bottom formula, you are not changing these numbers. You're flipping you will eventually have to flip that reaction, but using that second formula, you are not changing these numbers. In other words, you're subtracting a negative number instead of adding a positive number. Does that make sense to you all? Anybody confused by that? I'm hearing crickets, so I'm going to go on. Again, these two formulas are exactly the same. It's just in the top one, we are actually changing the sign of the reduction potential because we're adding the oxidation potential. In the bottom one, we are not changing the sign because we're subtracting the reduction potential at the anode. They're both the same formula. Remember, oxidation, loss of electrons. Oxidation occurs at the anode. Reduction is gain of electrons. That occurs at the cathode. If I didn't tell you this before, I'm telling you this now. Great mnemonic. Oxidation is a vowel, anode is a vowel. That's why you know they're together. Reduction is a consonant, cathode is a consonant. Or they begin with consonants. So you know that the cathode is where the reduction occurs. Now, if you have a positive E0, this means that your redox reaction will favor products. If you end up adding these numbers together, that means that the redox reaction will favor the reactants. In other words, it's how you write the equation. If you have a positive E0, this means you have put them in the right direction in order to produce products. If you add them up and you get a negative number, all this means is you just have to flip the entire reaction, because if you have a negative E0, this favors a spontaneous reaction towards the reactants. If you get a positive E0, the reaction will proceed in the direction written. Negative, it will not proceed. It will proceed in the opposite direction. Rules. If you flip the reaction, change the sign of the voltage. If the reaction is multiplied, do not multiply the voltage. The standard potential is an intrinsic property. That's why you do this. Okay, I have a zinc copper cell. For the oxidation, I have my E reduction is a negative 0.76. My E reduction for the copper is a positive 0.34. Which one am I going to flip? You had the right answer.
Do you wait? Do you flip the negative 0.76 since it's smaller?
Not since it's smaller, it's negative.
Or, yeah.
If I have a negative and a positive, I'm always going to flip the negative one
Okay.
because I want the final answer to be positive. That way I know that my reaction is going in the right direction.
Okay.
So I add my E reduction from my cathode. I add to the flipped reaction. Remember, when I flip it, I change it from a reduction into an oxidation. I add my cathode voltage to my oxidation of my zinc. I add those together. I get a standard cell potential of 1.10. Standard cell potentials. Let's see who's out there. Anaya, Araceli, Benita, Emily, and Jenna. You're going to add lead and zinc. I want to know what the standard cell potential is. Leonardo, again, lead plus zinc. And this is lead. This is going to be, the lead ion is a +2, zinc ion is a +2. Write this reaction down. Leonardo. Natalia, Natalie, Rhea, Sachari, Vanessa. I want you to do the second reaction. It's nickel +2. The nickel ion is going to be a +2 nickel. The aluminum is a +3. Ethan, Ethar, Jana, Manuel, Parker, and Vanessa. Do the last one. The last one is iron +3 plus tin +2. Now understand, the ions are going to be on either side of the arrow because we're turning one ion into a metal, the other metal we're turning into an ion. Okay, everybody has their assignments. Okay, there are the potentials. I want to know what the standard potential for those three cells are. I'll be back in 5.
Does anybody see lead?
Yeah, I don't see it either.
Okay, I didn't think so.
Professor?
Okay, what do we got? Who's got an answer for lead plus zinc?
Lead's not on the chart.
Ah, crap. Okay. Lead +2. I knew I was going to run into problems with that. Lead +2 plus 2 electrons has a standard potential of -0.13. So if lead is a -0.13 and zinc is a -0.76, which one am I going to have to flip?
Zinc.
So I add a positive 0.76 and a negative 0.13 to make a positive 0.63. Do we understand that, guys?
Yes.
Thank you. Second one. Who
I'm
had-
sorry.
Daniel?
Okay. I just want to ask, how did you determine? Could you explain one more time how you determined like
Okay.
which one to flip?
All right. When the reduction potential for lead +2 plus 2 electrons going to lead metal, that reduction potential is a -0.13. I have to figure out which one I'm going to flip so I get a positive answer. So, Manuel, if you want to write this down, if you have 2 negative potentials,
Okay.
choose the larger quantity to flip. Okay, Manuel?
Okay.
If you have 2 negative potentials. If you have 2 positive ones, you flip the smaller quantity one. If you have a positive and a negative, that one's easy. You always flip the negative potential. Okay? Make sense,
Could you repeat
Manuel?
the two? Yeah, could you repeat the 2 negatives one more time? If you have 2 negative
2
potentials.
negatives, the larger quantity. So like right there, that example, my lead was 0.13, my zinc was 0.76. I'm going to pick the larger quantity, the zinc.
Okay.
0.76 is larger than 0.13. So when I flip the zinc is a positive number that's larger than the negative quantity of the lead. If I have 2 positives, I'm going to flip the smaller quantity of the 2 positives. Because when I flip the smaller quantity, that turns into a negative number, and that's subtracted from the larger number that is positive. If I have a positive and a negative, I simply flip the negative number.
Okay. Thank you.
Now, second answer.
I got it.
What's the answer?
I got 1.38 because nickel was -0.28 and aluminum was -1.66. So I flipped the -1.66.
And you ended up with 1.38 or 36?
Yes. Yeah. 38.
1.38. All right, good. How about the last one?
I got 0.104.
0.01, I'm sorry. Give that again, Ether.
104.
0.104.
Yes.
And what were the 2 compounds?
So both will be negative, but we turned the -0.14 with a positive.
Where'd you get 0.014? What compounds are you flipping, Ether?
The SN.
SN's not in here. Okay. Ether must be looking at her book. Is that true?
Yes.
Sorry. Find the silly thing. There we go. You're exactly right, Ethar. 10 is a minus 0.14. And what was the other compound?
The other compound is negative 0.036.
It was 10 and what?
So the first one is negative 0.036, and the other will be 0.14.
So I've got my iron is a negative 0.036. My tin is a negative 0.14. I add those up. I flip the iron and add them up, and I do get a 0.104. Those are the two potentials. I'm flipping the more negative one, and I end up with a positive 0.63. This one, again, I've got two negative potentials. I'm flipping the higher one. That ends up with the 1.43. And again, I'm flipping the higher number. That gives me a positive 0.104. So when they are written like that, where I get a positive voltage, the reactions occur spontaneously. From a production of cell voltage, which is my best, which one will produce the most volts? Iron tin, nickel aluminum, or lead zinc? Lead zinc is a 0.63, nickel aluminum 1.43, tin iron 0.104.
Nickel aluminum.
Nickel aluminum has the best voltage. Again, oxidation occurs at the anode, loss of electrons, reduction, gain of electrodes, cathode. Guys, I'm repeating this several times. You need to have this information memorized.
I have a question. So the best voltage is nickel and aluminum just because it's the higher number?
Yes.
Okay, just to make sure.
It produces the most volts. Yes.
Okay, right.
Could you go back to that slide one more time? I just want to take a picture of it.
Which one? It's
That one. Yeah, to the
this one?
no. One more
This one?
forward.
This one?
No, not that one. One more forward. That one. All right, thank you.
Okay. I have copper and silver. Which one am I going to flip?
Do you flip the copper?
I'm flipping the copper because when I add them together, I want a positive value. Now look what happens when I flip them. I want a positive value. So I'm going to flip the copper. Look what happens when I flip them and add them. I have flipped these reactions. I know what my potential. Now, when I add these two reactions together, remember, these are only half reactions. What is actually happening in the reaction is I'm actually adding copper metal to a solution containing silver ion. I got copper ion being produced and silver metal. Remember, when I added these two together, I ended up getting a positive answer. So I know if I got a positive voltage, I know it goes in this direction from left to right. So what am I producing? Come on, guys. What's
Wait,
the product?
I actually have a question.
Okay, Manuel.
On the when you added the two reactions, you got copper plus 2Ag yields Cu2 plus Ag. Is that supposed to be a 2Ag by any chance? Because the half reaction for the second one, I just wanted to make sure. Sorry.
You are correct. You are correct, Manuel. It should have been a 2. Okay. Now, you notice I need to keep my electrons. I can't produce electrons without having them sucked up by something else. So when I have the two half reactions, I need to multiply the silver reaction by 2 to make sure that I absorb the electrons that are produced by copper. So that is why I have multiplied the silver half reaction by 2. But also notice, I did not increase the voltage. The voltage stayed the same. So now I add these two half reactions. The 2 electrons are going to cancel out. What do I produce?
Copper and 2 moles of Ag.
What form of copper?
Solid. I'm guessing at this point. I'm not too sure.
Manual, where are products? Are they on the right side of the arrow or the left side?
On the right.
So what am I producing?
I just said it. Copper and 2 moles of Ag. Or
I asked
Cu2.
what form the copper was in.
I guess solid. I'm not sure.
Manual, look at the products that are on the right side of the arrow.
Okay.
Am I producing copper metal?
No.
What am I producing?
Copper an aqueous copper solution.
What is it, ionic or is it neutral?
Oh, ionic.
Okay. Which metal ends up being ionic?
The copper.
Okay. When you were told single displacement reactions, you were always told the more active metal ends up ionic. So in this reaction, what ended up ionic?
The copper.
So which one is more active?
The copper.
So you can use, this is how they developed the activity series. They looked at the potentials and they put standard cells together. And they determined which direction the electrons flowed, and they determined which one was producing the ions. And they were able to now determine the activity between copper and silver, because copper ions are produced. Because I had to put the reaction in this direction to get a positive voltage. Because I had to put the reaction in this direction to get a positive voltage, I created copper ions. If I created copper ions, this means copper is more active than silver. So when predicting the activity series, we're going to compare the two half reactions. The more positive the reduction potential, the more likely that substance is going to be reduced. If the substance is reduced, then we're going from an ion gaining electrons into a neutral substance. If that substance is reduced, then it is less active than the metal that it is paired with. The more negative the reduction potential, the more likely the substance will be oxidized. If it is oxidized, that means it's likely that it became an ion, because oxidation is loss of electrons. I take a metal, I lose electrons, I create an ion. If the substance is oxidized, it is more active than the substance being reduced. I have a series of reduction potentials. Which of these metals is the most active?
Is it the copper?
Okay, if you had copper with, I don't know how that number got in there. If you have copper with iron, which one would you flip?
You said copper with what?
If you have copper with iron, which one do you flip?
Iron.
You flip the iron. So if you flip the iron, that means that you have iron going to iron plus 2 electrons. You have iron 0 going to iron plus 2 electrons, and you have copper plus 2 electrons going to copper metal. You said that you flipped the iron. So the iron is the one being oxidized. If the iron is being oxidized, we're creating an ion. Which one is more active, iron or copper?
The iron, because it's being oxidized.
Exactly. I'm taking my iron metal and making the iron out of it. Remember, we've defined most active as the one that produces the ions. So because we have flipped the iron to being oxidized, then the iron is going to be more active than the copper. Okay? We compare copper with zinc, iron with zinc. Which one are we going to flip?
Zinc.
If we flip the zinc, which one creates the ions? Is it going to be the zinc or the iron reaction?
The zinc.
So the zinc is creating ions. It's being oxidized. So between zinc and iron, which one is more active?
The zinc.
All right. I compare zinc with sodium. Which one do I flip?
The
Sodium.
sodium.
If I flip the sodium, do I create ions?
Yes.
If I create ions, is it more active?
Yes.
So we have just determined sodium is more active than zinc, which is more active than iron, which is more active than copper. The strongest oxidizers have the most, I'm sorry, I don't like this. Okay, I have to say it this way. There's no other way for me to put it. The strongest oxidizers are the compounds with the most potential to be reduced. So the compounds that have the most potential to be reduced have the most positive reduction potential. The strongest reducers, the strongest compounds that have the potential to be oxidized have the most negative reduction potentials. So if I am looking at a chart, remember, we've been all talking, we've been flipping it and talking that oxidations create ions. If oxidations create ions, then what is happening is the further you get down on this table, the more negative your result, the more active your metal is going to be. Let's just remember it as that. If you have a table of reduction potentials, the more negative your reduction potential, the more negative your reduction potential, the more likely your substance will be oxidized, which means it's more active. Are you good with that? Write that down. The more negative the reduction potential, the more likely your substance will be oxidized, the more active that substance is. So on this chart, fluorine is the least active, lithium is the most active. Any questions, ladies and gentlemen, about that? All right, we have to relate this. We have to relate electron potential back to free energy. And we do it by the equation delta G0 is equal to negative NFE. Remember, when do we say a reaction is spontaneous? What's the sign of delta G for a spontaneous reaction?
When it's positive.
When it's
What?
negative.
Negative.
I'll go with the two negatives over the one positive. When delta G is negative, you have a spontaneous reaction. So since delta G is equal to NFE, N is the number of electrons, which is always going to be a positive. F is a constant, which is a positive. That means when your E is positive, it's going to give you a negative delta G. This is why I've been harping on making your cell potential a positive number. Now, to define the equation further, N is going to be the number of moles of electrons transferred. F is going to be a constant. It's 96,485, which is the same thing as the labels are the same.
Wait, I have a question. So
I'm
you
here.
said E is positive, then delta G is going to be negative?
Because it's negative NFE. For a spontaneous reaction, delta G has to be negative. So in order to make delta G negative, E has to be positive.
Oh, okay. I see it. Yeah, so positive times negative is negative.
There we go. Under standard conditions, the standard Gibbs free energy is equal to negative NF times the standard cell potential. Consider the reaction. 2 aluminum plus 3 I2s yield 2 Al3 pluses plus 6 I minuses. What is the Gibbs free energy? Okay, you got F, that's a constant. you can go to the table and figure out what the potential for aluminum and the potential for iodine is, and you can determine what E0 is. You have to determine the number of electrons through the half reactions. Aluminum goes to Al plus 3 plus 3 electrons, and the I2 goes to 2I minus plus 2 electrons. Again, I cannot make, I'm sorry. Yeah. I cannot make electrons. I can't have electrons that are produced or absorbed up. I have to have an even number of electrons produced and absorbed. Aluminum produces 3, iodine produces 2. So I have to multiply the aluminum expression by 3. I have to multiply the iodine by 3 to get the electrons equal. So overall, how many electrons did this reaction produce and absorb? Guys, let me
Well, do they
explain
cancel
something.
out?
Sorry, I need to explain something. The longer you guys take to respond, I don't get over the material. The final is written. If I don't get over the material, then you're going to have to take the final without my having reviewed it. So please cooperate with me. I am really, really getting extremely frustrated with you all. Thank you, Manuel, for commenting. Manuel, how many electrons are being produced and absorbed?
If I'm looking at the bottom half reaction, 6 are being produced and then 6 are being absorbed.
So when I go to plug that into my formula, and again, my E cell is going to be 2.20 positive. Note, I did not increase the voltages because of multiplying the two equations. Those voltages stayed the same. So when I plug it into the equation, N was the number of balanced electrons that were transferred. I multiply that by my Faraday constant. I multiply that by 2.20 volts. I end up with 1,273 positive number. I'm sorry, it should be a negative number. Negative 1,273 kilojoules per mole. Is this reaction spontaneous?
Yes.
Yes, it's negative.
All right, strategy wise, you're either going to be given delta G or you're going to be given the anode and the cathode. If you're given delta G, you also need to be given how many electrons are being transferred. Normally speaking, though, when you see a problem like this, you will be given the half reactions and you will be given the standard reduction potentials. You determine which one you have to flip to get the E0. Then you balance the electrons to determine how many electrons are transferred. And you simply just multiply number of electrons transferred by Faraday's constant times the voltage. Notice that is in joules. delta G's are reported out in kilojoules. So the number I came by multiplying all this, I divided it by 1,000 joules per kilojoule. We also, in the last chapter, we determined that delta G is equal to negative RT ln of K. I just gave you a formula of delta G is equal to negative FE0. So if that is the case, then I have E0 by this manipulation is equal to RT ln of the K divided by NF. So I can use this reaction to either determine what the equilibrium constant is, or I can determine what the standard voltage of the cell is. At 25 degrees Celsius, T is equal to 298 K. R is a constant. R is a constant. F is a constant. I can change the ln value to log by multiplying the ln by 2.003. I determined a 2.3003. Therefore, I can simplify this relationship. I can simplify this relationship to E0 is equal to 0.0592. That's what all these numbers multiplied equal out to, divided by N times the log of my equilibrium constant. Did you all understand how I got this expression? Any questions on that?
I'm confused on the last part of the information you gave us, where it says and ln of K is equal to 2.303 log of K.
If you change an ln into an log, if you want to do that, the lnk is equal to 2.303 times the log of K. The original equation manual had the ln of K. I just changed this to log of K. If you want to change lnk into log of K, you have to multiply the log by 2.303. And that got incorporated with all the constants to equal this number 0.0592. What is K for the oxidation of nickel with tin? Okay. I have my equation. My E0 is equal to 0.0592 divided by N times the log of K. So I simply figure out what my E0 is. What is my E0 in this problem? What's my standard voltage?
.37.
No, I have to flip one, not two.
You have to flip the negative 0.23 and you would get 0.09.
Did you understand that? Whoever answered first, did you understand that?
Wait, what did she say?
Emily, you flip one reaction, not both, because you need
Oh,
an
yeah.
oxidation and reduction. So you're going to flip the larger negative answer. So you get 0.23 positive minus 0.14, that equals 0.09.
Okay.
Okay? And there are two electrons. Look. I am transferring 2 electrons. So my N is equal to 2. So I simply take my standard voltage, multiply that by 2, and divide by 0.0592. And for this, I get
Negative 3.04.
okay.
Yeah, I got that too.
Was E supposed to be positive or negative?
Okay. E is a positive number. So this should be positive.
Oh, okay.
So this is going to be 1096. Again, what I did to solve this, my overall equation is E is equal to RT times the L. E is equal to 0.0592 divided by N times the log of K. I have these two numbers. In order to get E0, I'm flipping the Ni. So my standard voltage is going to be 0.09, a positive 0.09. I'm transferring 2 electrons. So I have 0.09 is equal to 0.0592 divided by 2 times the log of K. This math ends up being a positive 0.304 is equal to log of K. 1096 is equal to K. So my equilibrium constant is 1096. Any questions, ladies and gentlemen?
How did you go from 3.04 to 1096?
How do you get rid of logs?
Is it elevating it?
You have to take 10 and raise it to that power. So 10 raised to the 3.04 is equal to K. 10
Right.
raised to the log goes away.
Right, the base.
Now, if you remember back, again, this is just last chapter. The Gibbs free energy at non-standard conditions is equal to Gibbs free energy at standard conditions plus RT times the ln of Q. Delta G under non-standard conditions is equal to negative NFE. That's the E at non-standard conditions. This means that my E at non-standard conditions, I'm going to divide both sides by negative NF. My E at non-standard conditions is equal to my voltage at standard conditions minus RT over NF times the ln of K. Again, ln of K can be converted to log of K by multiplying by 2.303. F is a constant, R is a constant. We're at 25 degrees, so T becomes a constant. This means that my equation becomes E is equal to E standard minus 0.0592 over N times the log of K. Calculate E for a silver copper cell containing 0.100 M Ag plus and 0.200 M copper 2 plus. And I need to put in another, calculate the E's at 25 centigrade. I'm no longer under standard conditions because I'm no longer at 1 molar silver plus and 1 molar copper plus. Strategy. I'm going to employ the Nernst equation. I know I can look at a table and I can come up with an E0. I can manipulate the half reactions to determine how many electrons are transferred. I also have the concentrations. I can determine what Q is. So I can determine E0, I can determine N, and I can determine Q. It's going to be very important solving these problems to flip the right reaction, because if you don't flip the right reaction, then Q is going to be the inverse number. Okay, I have Cu Cu 2 plus 2 electrons going to Cu is a positive 0.34 volts. Ag plus 1 electron going to Ag is a positive 0.80 volts. Which one am I going to flip?
The copper.
All right, so if I flip the copper, I'm going to have copper metal going to copper plus 2 electrons. What am I going to have to do to balance the electrons?
Multiply by 2.
Multiply which reaction by 2?
The silver one.
Okay, so I've got my copper reaction and my silver reaction. My copper is being oxidized, my silver is being reduced. So I have to multiply the silver by 2. Now I have to add both of those reactions. When I add both of those reactions, my product is 1 copper. My reactant is 2 silvers. Remember back to equilibrium equations. Equilibrium expressions. Do I ever use solids in it?
No.
So what is the equilibrium expression for that reaction?
Would it be copper over Ag? Over silver?
Almost. Almost. What's the coefficient in front of silver?
Right. So silver would be squared.
Copper over silver squared.
Mhm.
Okay, I flipped my copper because by flipping the copper, I end up with a positive number. That means my copper is being oxidized. That means that my half reaction is what you just said it was. Now, how many, sorry. Sorry, I need to go back one slide. Now I gotta need to go back. I swear to God, I had that slide. All right. These are the half reactions. Tell me how many electrons are being transferred?
2.
So the N in my Nernst equation is going to be 2. My E0, we just figured out, is going to be a positive 0.6. Now we got to figure out what Q is. And I think it was Natalia. Did you answer the question?
Yes.
I'm putting copper concentration over silver concentration squared. And if we look back at the original problem, my copper was 0.2 molar, my silver is 0.1. So to get my concentration of to get my concentration of copper, I put that over 0.1 squared, which is the concentration of silver. I plug everything in. My E cell is going to be my E standard minus 0.0592 divided by my number of electrons, which was 2, times the log of Q, which is 0.200 divided by 0.1 squared. I do that math out. I end up with this number being a 0.04 volts. I subtract that from my 0.46 volts. My E of cell has been reduced by 0.42 because my concentrations have changed. Any questions? This is probably the hardest question you're going to answer in this chapter. Strategy-wise, let's go back to the beginning to strategize as to how we are going to solve this problem. That's the original problem. That's all you're given. Okay, you're given this and you're given the Nernst equation, which means the E of your cell is equal to the standard cell potential minus 0.0592 divided by number of electrons times the log of Q. You know what the cell is. If you know what the cell is, then you can go to a reduction potential table and get the reduction potentials, and you can determine E0 cell. You can look at the half reactions. You're going to have to flip one of the half reactions, and you're going to have to flip it so that you get a positive E0 cell. After you flip it, you got to multiply so that you even out the electrons. Now, you're going to add the two half reactions, and you're going to determine the ion that's produced, and you're going to divide that by the ion that you started with. That's based upon adding the two half reactions. You know that Q is going to be equal to the concentration of your ion product raised to its coefficient divided by the concentration of the ion reactant raised to its coefficient exponent. Then all you do is plug the numbers into the Nernst equation and you're solving for E0. Another thing I want to point out to you. Sorry, I'm getting to the number, getting to the final solution. Guys, I've got 0.052. That's going to be divided by a whole number. Generally speaking, it's going to be a number between like 2 and 10. So I'm dividing by a whole number. So this small number becomes even smaller. And I'm multiplying that by a log. Now, in order for that log to be significant, like the log of, if the log has to be a number of 10, you have to understand that the difference between these concentration has to be 1,000,000,000,000 to 1 in order for that to be, in order for the log to be 10. So what I'm trying to tell you is this second term is going to be small. It's going to be somewhere in terms of being in the hundredths of a volt. So in effect, it doesn't have much effect, but it does have effect. Now let's look back. Let's look back at the Nernst equation. Okay. What happens if my anode and cathode involve the same reduction reaction? In other words, I have, say, copper on one side, copper on the other. What do you think my E0 voltage, my E standard voltage is going to be for copper electrodes on both sides? Remember, I'm taking E reduction minus E oxidation. So aren't those numbers going to be the same?
So would the E end up being just 0?
The E0 is going to be 0. Now, Parker, work with me here for a second. If E0 is 0, is there a chance that the second half of this is not going to be 0? Parker?
I'm thinking. I mean, no, it couldn't be 0, right?
Well, it could be 0 if Q is equal to 1, right?
Yeah. Okay.
If Q is equal to 1, then the second term is going to be 0. But if Q does not equal 1, is this second term going to add value?
No.
If Q is not 1, don't we have a number here for the second term?
Yeah.
It equals a number other than 0, right?
Yes.
So if I got a number other than 0, then my E cell is not 0.
Yeah,
So
yeah.
What I'm trying to get you to understand, if I mess with the concentrations, even though my standard reduction and my standard oxidation are the same, if both electrodes are copper, I can still create a voltage if I change the concentrations of the two solutions. And that is called a concentration cell. If I have nickel on both sides, notice that the E0 cell is going to be 0. But because the concentrations are not the same, my Q is not going to be 1. My Q is going to give me a number. Now, remember that E has to be positive in order to make delta G negative. All right, we're going to work our way through this. How do I make E positive? What does the value of the log of Q have to be? Does it have to be bigger than 1 or less than 1?
Bigger.
If it's bigger than 1, what's the log of 10?
1.
Positive 1, right?
Mm-hmm.
What's the log of 0.1?
10.
Nope,
I mean,
-1.
oh, true. Because
So my Q has to be less than 0. My Q has to be less than 0 in order to be a positive E. So that means when I'm dealing with a concentration cell, my dilute sample, my dilute concentration is going to go above my concentrated sample solution. Has to be. When you're doing a concentration cell problem, the dilute has to be above the concentrated. So I have a copper. Okay. Am I going to get a very big voltage from a concentration cell? I'm multiplying 0.0592, dividing that by a whole number, and multiplying it by a log that is not going to be greater than 10. Am I going to have a whole lot of voltage produced?
No.
No.
All right, so if you are dealing with a concentration cell, know that E0 is equal to 0. You're going to have negative 0.0592 divided by, again, I'm looking at the number of electrons transferred. I've got Ni plus 2 going to Ni metal. I am gaining 2 electrons. 2 electrons are being transferred. So I'm dividing it by the number of electrons to make the ion into a neutral metal. I am multiplying that by the log of Q. My dilute sample is going to go atop my concentrated sample. Find E0, delta G0, and K for the following cell. I got to come up with my relevant reactions. I'm not going to give it to you in this form. What I would do is I would give you the half reactions. These are the 2 half reactions. The copper has already been flipped. So what is my E0 cell?
Is it 0.109?
0.109. All I'm doing is just adding the oxidation with the reduction. Okay? But again, I have a disproportionate amount of electrons. So what do I have to do to make the electrons transferred equal?
You have to multiply the equation to match up the number of electrons.
I have to multiply the top equation by 2 to match the electrons. Notice the E0s did not change. I add the 2 reactions up, and I end up with H2SO3 plus 4 H pluses plus 2 Cus yield 2 Cu plus 2s plus 2 plus sulfur plus 3 waters. My E0 cell is 0.109 volts. Delta G is equal to negative NF E0 cell. 4 electrons were transferred. I've got my F constant being that multiplied by my E0. I get negative 42.1 kilojoules point per mole. Remember, delta G is always reported out in kilojoules per mole. To get K, I just multiplied delta G is equal to negative RT times the ln of K. So K is equal to the inverse log of my delta G divided by RT. I just figured out what delta G was. R is 8.314. I need to change this 8.314 to kilojoules to match that. And that gets multiplied by 298. I do this math out, and my K is equal to 2.40 e to the 7th. Summary of signs and what the magnitude indicates. For spontaneous reactions, delta G less than 0. K is greater than 1. E0 is greater than 1. For non-spontaneous reactions, the exact opposite. Delta G is greater than 0, K is less than 1, and E is less than 0. I have a couple more problems solved, but ladies and gentlemen, I have to get on to nuclear chemistry. Any questions about electrochemistry? The other problems that are there are similar problems to ones that we've solved. If you want another example to work your way through, it's provided for you. Any questions about electrochemistry?
No, I think we're good.
Okay. Show all windows. Okay. Segue. We're going to be dealing with radioactivity and what happens. We are no longer dealing with normal exothermic reactions. We're dealing with reactions that are enormously energetic. And we're going to discuss all the chapters that we've dealt with up to this point are going to apply to nuclear chemistry. We're going to talk about the types of radioactivity. We're going to predict the type of radioactivity. We're going to deal with kinetics. We're going to deal with half-lives. We are going to deal with the integrated rate law, carbon dating, mass defect, nuclear binding energy. The two big problems we have to get through are three big problems. Half-lives, integrated rate law, and carbon dating are the same basic thing. And we have to deal with mass defect and nuclear binding energy. We will get through this, ladies and gentlemen. Now, if we're dealing with the nucleus, typically it's demonstrated in this fashion. You have the mass number, which is generally displayed to the top and left of the symbol. The atomic number is generally going to be to the bottom left. Or you may see this just displayed as C-12, or the symbol written out, or the element written out, carbon 12. We have to remember that nucleus is comprised of what we're going to call two nucleons, the proton and the neutron. Number of protons is the atomic number. Number of neutrons we obtain by taking the mass number, protons plus neutrons, minus the atomic number. because there are isotopes, not all atoms of the same element have the same mass due to the different number of neutrons in those atoms. I don't know if your professor ever told you. I'll throw this question out there. What's the purpose of a neutron? An electron,
to-
go for
oh,
it.
sorry.
Go ahead,
I was
Manuel.
just, I'm pretty sure a neutron attaches to a proton to make it stable.
Okay,
Something around those lines.
let's think about this, Manuel. If you have two positive things together, how are you going to stick those things together? The positive charges are going to push them away, right?
Mm-hmm.
So what you need to
Oh,
do
wait,
is you
a
need to,
neutron's negative, right? No, that's an electron. Electrons are negative. Neutrons are neutral, right?
neutrons are neutral.
Okay. Yeah.
So what you're trying to do is you're trying to stick the neutrons in there to kind of separate the protons away from one another. And yet, because one body has an attraction for another body, those two things get attracted and there's an energy keeping them together. The energy keeping those bodies together overcomes the positive repulsion. And that's why the nucleus is able to stay together. So different atoms of the same element can have different numbers of nucleus, which results in different masses. There are actually three. Go ahead, Manuel.
Oh, I'm sorry. I sent you a direct message through Zoom. Whenever you get the chance to read it, I'm sorry. I didn't mean to interrupt.
I'm sorry. Is it in chat?
Yes.
I can't. I have to get out of, in order for me to see chat.
Okay, I got you. I'm sorry. I just sent you a message.
Good
saying
enough.
I
Good
had
enough.
to-
Manuel,
Okay.
just look at the end of the video.
Okay. All right. Thank you.
So if I'm talking about uranium, I have three naturally occurring isotopes. Uranium with the mass number 234, 235, or 238. Now, what happens is sometimes we can put the wrong number of neutrons into the nucleus. And that makes the nucleus unstable or radioactive. We refer to those kind of atoms as radionuclides. And there are several ways that a radionuclide can decay into a different nuclide. Ultimately, what they're trying to do is these radioactive atoms are trying to lose electrons, gain protons, gain neutrons, lose neutrons. They're trying to do that in order to have a stable ratio of neutrons to protons. If we have alpha decay, we lose an alpha particle. An alpha particle is basically a helium nucleus with a mass of 4 and an atomic number of 2. So if I have uranium 238, the mass number of uranium 238 is 238. The atomic number is 92. If it decomposes and makes a helium particle, an alpha particle, then I have to subtract 4 from the mass number because it created helium with a mass of 4. So my new element is going to have 234 because 234 and 4 equal 238. And it's also lost 2 protons. So if it started with 92, it lost 2, it now has 90. Whatever is on the right side of the arrow has to equal the left side. If I lose a beta particle is a high energy electron. Remember, electrons do not have any mass. They have no mass, but they have a -1 charge. So basically what happens is a neutron is losing an electron and converting into being a proton. You will see a beta particle either with the beta symbol or illustrated with a 0, -1 for an electron. Again, left side has to equal the right side. Since the electron has no mass, the element I've created will have the same mass number as what I started with. But the electron has a -1 charge. What this means is that I had to gain a proton so that the left side protons added up equals the right side added up equals the left side. Questions on this? Questions on this, ladies and gentlemen? Vanessa, I didn't get your question.
No questions.
I'm sorry. All right. If I have a positron decay, I have a particle that has the same mass of an electron, but it has an opposite charge. So instead of losing a -1, I gain a charge for my positron particle. Basically, what happens is a proton gets converted to a neutron and a positron. Again, my numbers on the right side of the equation must equal the numbers on the left. So if my positron is 0, +1, then my mass number is going to be the same, but I will have lost a proton. Again, is this making sense, guys? If I have gamma emission, gamma rays are high energy radiation. There is no loss of neutrons or protons. So I start with my isotope, I get that same isotope back, and I generate gamma rays. If I get an electron capture, it's the same basic thing as a positron, only in this case, the proton grabs an electron and creates a neutron. There is no real difference in the equation between an electron capture and a positron emission. Bottom line, proton gets converted into a neutron. So to do these problems, you have to remember that the mass number is going to be equal to, the number of neutrons is going to be equal to the mass number minus the number of protons. You're going to be given the atomic symbol, so you're going to know how many protons you have. In order to determine the number of neutrons, you have to know the mass number and the element itself. Calcium 46 undergoes beta decay. What new element is formed? Did I lose any mass?
No.
So my mass number is still going to be 46. Did I lose or gain a proton?
You gained a proton since it's beta decay.
Remember, left side has to equal the right side. So my number of protons has to be one more than the protons I originally had. So I make, I don't even know what that is. I make scandium. I make scandium 46. Questions about that, ladies and gentlemen? Francium 221 has to undergo what type of radioactive decay to create astatine 217? All right. The 221 is my mass number of francium. My astatine mass number is 217. So francium created astatine. The particle it created has a mass number of what?
$217.
217 is what the astatine weighs. Francium weighs 221. So what's missing?
Four.
4. So the particle I'm created has a mass number of 4. Now, if we go to the periodic table and I look at the atomic number for francium, it is 87. Astatine has a mass number of 85. So if we're going from 87 to 85 protons, the particle that I've created has how many protons?
2.
2. So what has a mass number of 4 and a proton number of 2?
Helium.
Helium. So I have undergone alpha decay. So my francium got converted to astatine, and helium was also created. So guys, just write the equation. All you're really doing is you are looking at the particle you're given and you're looking at what you started from. Then all you're doing is subtracting the mass numbers and the number of protons. And that will determine what type of decay or what element you are creating. Parker.
Yeah, I'm here.
Okay, that's not what I wanted. Okay, are you seeing the first one? Parker,
Can you hear me now?
you have the first, you see the first reaction?
The lead, right?
Yes.
Okay.
Lead underwent beta decay. What was the element that was created? What is its mass?
So for beta decay, is it gonna be 210 for the mass?
What's the mass of a beta particle?
Oh, it's 0 because it's an electron, right?
Mm-hmm.
Okay, so
So,
that's 0.
so it adds 0. So what's the mass of this particle that's in question, Mark?
Still 211.
Still 211. How many protons do I now have?
I have
plus
one less.
Nope. What
Oh, no,
plus what plus a -1 equals 82?
83.
83.
So it
So my
is-
particle is going to weigh 211, and it's going to have a mass number, atomic number of 83. So that is going to be bismuth. Okay. What time are we at, guys? I don't have my watch on.
1211.
Okay, good. I'll get through at least these. Okay. Let's see who else is out there. Sachari,
Yes.
I've got bismuth going to whatever TL is. I never have these. That is thallium. Bismuth 214 goes to thallium 210. What type of decay?
I'm sorry. What kind of decay?
What kind of decay? What particle did I produce? What does it weigh?
The 210?
Nope. I'm asking you the particle that gets produced with the thallium. Thallium is produced. What else is produced with the thallium?
Is it helium?
I've got, what does it weigh, Sachari?
210?
Nope. What's missing here? Remember, left side has to equal right side.
Mm-hmm.
So what mass?
You're missing 4?
So that's my particle that's missing weighs 4, has 4 mass numbers.
Mm-hmm.
How many protons does it have?
2?
It has 2 protons. So as you said, it is a helium particle. Helium particles are alpha decay.
Mm-hmm.
Ria,
Yes.
okay. I started off with something and I ended up with Pa 234 plus a beta particle. What did my original substance, what was the mass number of my original substance?
234.
234. What was its atomic number?
991.
Remember, whatever is on the right side has to equal what's on the left side.
Oh, 92. Or
Rhea,
90.
which is it, Rhea?
I don't know.
Come on, Rhea, add these numbers up. What's 91 and a -1?
90.
90. So my compound weighs 234. It has an atomic number of 90, which is thorium. Anaya. Anaya?
Yes.
Okay. Anaya.
Hmm.
Something underwent gamma radiation and left me 10-219. What did it start out as?
are you asking for the atomic number?
Yeah, atomic number and the atomic weight.
Is it 219?
219 is the weight. What's the compound?
Is it not SN?
Absolutely. It is SN. Gamma radiation doesn't have any weight, doesn't have any protons. So what happens is my 219 SN,
Okay, it stays the same
it
because
stays the same, but it releases radioactive energy.
okay.
Okay. I'm going to go back into, I'm going to end show because I need to put some weights in here. Or some atomic numbers. NP. NP is neptunium. It has an atomic number of 93. Okay. And Pu is plutonium. It has an atomic number of 94. Okay. All right, I've got neptunium going to plutonium. I want to know what type of radiation or what type of decay it underwent. What is the mass?
It's the same.
Same. So I have a mass of,
0.
nope. Oh yeah, very good. Yeah, I'm sorry. I'm getting tired. After 2 hours, I get tired. I'm sorry. Okay, now, what is the number of protons?
-1.
Very good. Who answered that?
Natalia.
Thank you, Natalia. Very good. So, what kind of radiation?
Beta.
Beta radiation. All right. I have a positron that's created. I have a positron that's created, and I want to know sodium has 11 protons. It has a mass number of 22. What did I create?
Neon.
Absolutely. And what's the weight of it? What's the mass number?
Isn't it still 22?
Exactly. And answers follow. Okay. Let me.
What's the K for?
The K? What K?
Yeah, the first couple ones.
Uh,
In the-
nothing.
Oh, okay. Okay.
No idea how that got in there. All right, let me just want to run through some things. Okay, let me. Okay. I'm trying to figure out whether I want to do something more. I think we'll be okay, guys. We will get through the rest of it on Thursday. Any questions about either electrochemistry or nuclear chemistry? We have about We have about 60 slides to go and we are done. Any questions, ladies and gentlemen? Do your best to get this stuff down. Do your best to get that stuff down. I believe that I have given you some worksheets in that regard that are better than the Pearson. So I'm just looking it up here just to see. These are actually problems from your book. And if you notice, there are some, and they do have answers after them. I've got the problems here, and the answers follow. Okay? So I would go through and do these problems. All right, that's all I have, guys. I will see you on Thursday. I will see 5 of you this afternoon for presentations. Questions, guys? Okay. That's all I got for you. Take care, Ethan.